Okay, welcome everyone to Guided Study Group week 10 of Math 141 this semester. So I hope everyone has a very nice and relaxing break. So this is week 10 and also the last week before our midterm 2. So the materials right now, it doesn't really have anything new, but we're just gonna kind of like start to make applications of everything that we've learned so far from midterm 2, including everything related to, all features of the graph, like maximum, minimum, extreme values, how to find first, second derivative, concavity, inflection points, and all of that. And there's just one new piece of that is section 3.4, which we're gonna go over today, 3.4 and 3.5. 3.4 is basically just showing us how to find horizontal asymptote by finding the limit at infinity. And so there's one thing that I want to note here. For horizontal asymptote, I would write it abbreviated as HA, and then vertical asymptote, which is VA, is when you find the limit of x approaching plus and minus infinity. So two limit that you have to find here of fx. Is it gonna be a number or not? And the second one is VA, where you find limit of x approaching a of fx. So say if this thing is plus or minus infinity or does not exist, it means that you have a vertical asymptote. This thing we already go over at I think the beginning of this midterm 2 materials, but horizontal asymptote is what we're actually gonna touch on now. So if you find the limit of x approaching infinity or negative infinity of fx, and you get that equal to a value L. And note the fact that they don't have to be the same. Say if you have limit of x approaching infinity of fx is A, and limit of x approaching negative infinity of fx is B. Both of them y equal A and then y equal B. Both lines are going to be horizontal asymptote. So you can have more than one horizontal asymptote. So that's the definition of horizontal asymptote. There's something to note here, especially when you have the limit of x approaching plus or minus infinity of, say you have a square root of x squared over x. So a square root of an even function over x. So the thing is that when you have x approaching infinity, this is a positive number. So when you take it out of this x, take x squared out of this square root to kind of like cancel out the x in the denominator, which we try to do a lot of times, just to take like the highest power in the numerator and highest power in the denominator to kind of like cancel out one another to find the limit at infinity. And so this one, when you take it out, is going to be x1 plus something else of the thing inside of, say you have here plus something divided by x. So these two cancel out. So that makes sense. However, when you have limit of x, the same thing, but x approaching negative infinity. So this is the negative number. So we have defined before, when you have square root of x squared, is going to equal x if x is bigger than or equal to 0. Negative x if x is smaller than 0. Basically, we say the square root of something must always be a positive number. When x is smaller than 0, it has to be equal negative x, so that this thing is positive. So here it's going to be, when you take it out, it's going to be limit x approaching negative infinity of negative x, square root of that, over x. So when you try to cancel out, you have this extra negative out there, which didn't happen, which was not given in the problem statement. So just make sure that you be careful with that, especially when you have square root of an even power of x. So that is the definition and something to note about. Then we have a theorem. This theorem saying if you have r bigger than 0 is a rational number, then limit of x approaching infinity of 1 over x to the r is 0. And so this is easy. When you say here you have r bigger than 0, so you have maybe limit of x approaching infinity of 1 over square root of x is 1 over infinity is 0 for sure, or limit of x approaching infinity of 1 over x squared or x cubed is 0. So that's easy to see. However, when you have r bigger than 0, but limit of x approaching negative infinity, now that's when you have this extra conditions such that x to the r is defined for all x. This is because now you have a negative number. So if you have like a power, say this one, when you have square root of x is x to the half, right? So half is still bigger than 0. But you cannot have square root of x here because now it's approaching a negative number. So this won't work, but you can have like x squared, it might work, or cubic root of x, it will work. So make sure that you see that all the conditions are satisfied. So that is the materials I have for section 3.4. It's nothing really new for you, especially when you already take a calculus in high school. You should be familiar with all of the definitions and concepts of horizontal and vertical asymptote. And there's one more thing what we're going to touch on in 3.5, curve sketching, when we have slant asymptote. So slant asymptote is kind of like an expansion of horizontal asymptote. It's a little bit different, but it's just kind of require a little bit of more algebra when we have to touch on the skill of doing long division. But we're gonna touch on that in 3.5. So first example is question A of this section. So evaluate the limit and justify each step. So you have limit of x approaching infinity of square root of 9x cubed plus ax minus 4. X cubed minus 3x plus 3. So this is just like an exercise of finding horizontal asymptote for this function. So as I said, when x approaching infinity, you have this be a positive number. So it's okay for you to just now, and then you also look at the highest power in both the numerator and denominator. So because the highest power is this one, is going to be 3/2 because you have 3 and then with the square root, and then the same thing for the denominator. So you can take x cubed out to kind of like cancel out things. So you have this, take x cubed out. What do you have? So this is 9. It's going to be a over x squared. Because a over x squared multiply x cubed, you're going to have ax as initially. 4 over x cubed divided by x cubed. 1 minus 5 over x squared plus 3 over x cubed. Now these two can cancel out. And especially you don't need to care that much about, because the highest power in the numerator and denominator are equal. If they're not equal, whatever left, you have to be careful with if x approaching positive or negative infinity. In this case, because x approaching positive infinity, things are getting much more easier. And you have limit of x approaching infinity, square root of this, 9 plus a over x squared minus 4 over x cubed divided by 1 minus 5 over x plus 3 over x cubed. And as I said, limit of x when x approaching infinity, in the theorem that we have just now, this one is approaching 0. This one is approaching 0 because it's 4 over infinity, a definite number divided by a very big number, so it's 0. The limit of x approaching infinity of that expression is 0. So what we have left is just limit of x approaching infinity, square root of 9 over 1, which is just going to be 3. So I will justify through every step, because just a very small mistake can get you in troubles. And now I would say, when we're done with this example, when you want to do more practice, when you look in the book, try to find those that have limit of x approaching negative infinity. That is one. And limit whatever the expression inside, it doesn't have the highest power here equal to the highest power here. So these two should be different power so that it kind of like give you more exposure to what all kind of range of the things that we can expect in the exam. So that is example 1. Then we have example 2. So now we're going to find both the horizontal and vertical asymptotes. And remember, as I just mentioned briefly at the beginning of this section, for horizontal asymptote is when you find limit of x approaching plus or minus infinity of fx. And vertical asymptotes is where you find limit of x approaching a of fx, where a is like one of the number that x is not defined, something like that. So vertical asymptote first, because we learned that thing before. Now you look at this is a rational function. So whatever a value that you try to pick, you have to look at the denominator. So domain of f is d equal every point in R except for when you have x squared, except for the value of x that you have x squared minus 6x plus 5 equal to 0. Now you solve for that. X squared minus 6x plus 5 equal to 0. This one is going to equal x squared minus x minus plus 5 minus 5x minus 5 equals. So what we have eventually is just x equal 1 and 5. So now we have that. So the two special values that we're going to look at is a is going to equal 1 and 5. So you have limit x approaching 1 minus of fx. So this one is when we have limit x approaching 1 minus x cubed over minus x over x minus 1, x minus 5. One thing you also should know is that you can still factor out the numerator. So you have x. Inside you're going to have x squared minus 1, x minus 1, x minus 5. So what we have now is limit of x approaching 1 minus x minus 1, x plus 1. So now you can cancel out something. Because x approaching only 1 minus, it's not equal to 1 minus or 1. So you can just cross these two. So you have limit x approaching 1 minus x plus 1, x minus 5. So now when you plug in 1 minus, what you have here is 1 multiplied by 2 divided by negative 3. So it's going to be negative 2 over 3. So this is not positive or negative infinity. So, and then if you do the same thing for limit of x approaching 1 plus of fx, then you're going to have the same thing. Then you say vertical asymptote is not at x equal 1, because it doesn't give you the limit equal to positive or minus infinity. If we do the same thing for x approaching 5 minus, so what we end up having, so we can cancel out x minus 1 again, because now we're not at 1 at all, we're at 5. So what we have left is that this one is going to be 0 minus, and this one is going to be 5, and then 6 is 30. So 30 over 0 minus. So a definite number divided by a very small negative number. So this one is going to give us something negative and very big, because it's divided by a very small number. So the answer is going to blow up. So it's going to be negative infinity. Same thing if you do it for x approaching 5 plus fx. You're going to have it equal positive infinity. So you have vertical asymptote is going to be x equal to 5. Now we do horizontal asymptote. I think I didn't create enough space here. So horizontal asymptote is when you take it from approaching infinity of fx is going to be limit of x approaching infinity, x cubed minus x divided by x squared minus 6x plus 5. So you have this limit. Now if you look at the power in the numerator and denominator, again, it's kind of like give you a hint, especially when they ask you only to find horizontal, is that here you look at the numerator, highest power is the third power, but in the denominator it's a square. So the numerator always gonna blow up more than, it's always gonna be bigger than the denominator. And especially when x approaching infinity, you can do this. Take x squared out of both. You have x squared, x inside minus x minus 1 over x squared, 1 minus 1 over x. And you have x squared out, you have 1 minus 6 over x plus 5 over x squared. Now, you can cancel out the x squared, and what you have left is just this over this. Now, if you look at it, you have infinity in the denominator, and this thing approaching 0. Over, kind of like this one is 0, this one is 0, and this is 1. Infinity over 1, what do you have? So this is infinity. And if you do the same for negative infinity, you're going to get negative infinity as well. So our answer is no horizontal asymptote. If you find limit of x approaching negative infinity of fx, it is going to be negative infinity. And note the fact that we can only have horizontal asymptote if this limit gives us a number. If it's positive or negative infinity, we conclude the fact that it doesn't have horizontal asymptote. And actually, this one is going to have a slant asymptote, which we're going to see. If you have like, kind of like, you've already seen the lectures for 3.5, right? So you guys can definitely use like after I finish this, and maybe if you want some extra practice, try to find the slant asymptote for this. That will be a very good practice, especially when here you see a rational function. So that's like the general case where you can see a slant asymptote. Finally, this is example 3 of it's question 50 of section 3.4. Find the horizontal asymptotes and use them with a concavity and interval of increasing and decreasing. Sketch the curve. So this is kind of like a challenging one because it involves a lot of things. You find a horizontal asymptote, you sketch them with concavity and intervals of increase and decrease. So it's kind of like similar to 3.5 in the sense that you start to put things together. Not everything yet, but you have put like most of the thing. So first, horizontal asymptote. So you have y equal x over square root of x squared plus 1. So here, domain is everywhere because the denominator is always positive. So now, you have horizontal asymptotes when you put approaching infinity x over square root of x minus 1. Now this is where I have the note earlier comes into place, because now you want to take x out, the highest power of both of them out, and they happen to have like the same. And usually those things are not like, you shouldn't be asking like, okay, how do I know that? Well, math is the same of a lot of other sciences in the sense that it is a basic of many other mathematical and physical sciences, but it also have a sense of experimental. So everything usually is just come a lot from, well, you have to look at that, see like which way you can go around with it. If you do math with a lot of like intuition and like flexibility, it's so much better than just remember the formula and apply it in, because it's the same thing with engineering. It's all about like, being able to have the intuition when you see the problem and figure out like many different ways to solve it. Yeah, if engineering is just like, and math is just, learn by heart the formula and put it in, then everyone will be like a master of that. So I would say here, when after you take x out, and especially when x approaching infinity here, it's a positive number. So when you take it out of the square root, it's an x, not negative x. So you have 1 over square root of 1 plus 1 over x squared. Again, this one is 0 as x approaching infinity, so it's just going to be 1. And if you do limit of x approaching negative infinity, so again, as I said, that's a special point where you have to take note that is you're going to have x over negative x square root of 1 plus 1 over x squared. This is where you have 1 over negative 1 square root of 1 plus 1 over x squared, which is going to be negative 1. So our conclusion is that we have two horizontal asymptotes, y equal 1 and y as x approaching infinity, or y equal negative 1 as x approaching negative infinity. So now we have horizontal asymptote. Now we need concavity and interval of increase and decrease, which is gonna come back to our first and second derivative. So you have f prime of x. You're gonna have x squared plus 1. So I'm gonna quickly find the derivative here. So this is going to give us x. So again, now you see denominator is always positive and numerator is just 1. So this entire thing is always gonna be positive. So this is always increasing. So concavity, second derivative. So when you have 3/2 x squared plus 1 to the negative 5 over 2 2x. So this one's when you have negative 3x over x squared plus 1 to the 5 over 2. So again, denominator is always positive. So when you solve for this, this is going to be negative when you have x is positive, because x positive, this in the numerator you have a negative number equal to 0 at x equal to 0, bigger than 0 when x is smaller than 0. So easy, you can see concave upward on negative infinity to 0, concave downward on 0 to infinity, and inflection point at x equals 0. So you're gonna draw the graph now. So here you have that. So you see the fact that it's always increasing, and your formula is x over square root of x squared plus 1. So, and then you have two horizontal asymptotes at y equal, this is 1, y equal 1, and then y, and this is negative 1. Because our function can only be increasing, it will be from here. So the tail is here and this tail is here. You know the fact that you cannot have like a tail below here and go up, or up here, because if you have a tail up here, it's gonna have to go up and decrease. But our function only increase, so this part is not right. Again, and then when you have down here, because this is a continuous function on all points, because we have identified that the domain is R. So it cannot cross the line here, because we have just identified the fact that it has a horizontal asymptote here, so it has no value up there. So this thing is also wrong. And then when you look at this function, when x equals 0, y equals 0, so it crosses this point. So just generally, it can give us the idea that the graph is going to look something like this. But we're just going to make sure again. So we have it always increasing, satisfy. We have the horizontal asymptote as satisfy, so we only have concavity left. So concavity is saying it's concave upward on negative infinity to 0 and concave downward on the right. So what we do now, so I'll delete these two so not to confuse you guys. So this one is going to be concave upward, and then this one is concave downward. So this is our graph of the function, just based on concavity inflection point, especially we have inflection point here. It's exactly show the fact that we have an inflection point. I'll draw it in a more symmetric way. Okay, yeah. So that is our function. Inflection points here. This is concave upward. This is concave downward. You have an increasing function. You have horizontal asymptote at y equal 1 and y equal -1. And this is continuous on negative infinity to positive infinity. So it doesn't have, it cannot cross this, as I said, because it's a horizontal asymptote. You don't have any value on -1. It cannot be up here because it's gonna have to increase and then decrease to get this shape, like not this. So that's all I have for section 3.4. Now we're gonna go to section 3.5. So 3.5 is really nothing new. It's just when you start to put everything on a graph by, like derive all of them mathematically and then put them on the same page and on the same graph. So checklist, I would say I think the lecture notes is very, very helpful to capture all of this, so I wouldn't come to like review or like repeat any of them because I think she mentions all of the fact that we need. So I'm just putting a checklist here so that every single time you do a curve sketching or when you ask like, okay, what graph is this curve given this function, then you should make sure that you go through all of these and make your life easier, because this will give you all the information you need to identify the graph or sketch the graph. So on the time, find the domain, the y and x intercept. So this is very basic, just from high school. You don't even need to take this class to know that. Then you need symmetry. Is it odd, even, and periodic? And to figure out which one is which, I would highly recommend look at the lecture notes. Then we find asymptote, vertical, horizontal, and slant. The slant asymptote we're going to quickly cover down here, but just put it there first when we finish this checklist. Interval of increasing and decreasing. Use the first derivative. Figure out which interval is going to have first derivative positive is increasing, first derivative negative is going to be decreasing. Local maximum and minimum. You have first and second derivative. But I usually just use first derivative test. Points where f prime of x change the size. So like this, positive, negative, positive. So this is f prime. So your function of f is going to be increasing, decreasing, increasing. This is max, and this is minimum. This is an easy function to remember. Easy kind of like figure to remember. Concavity, inflection point, everything based on second derivative, and especially remember inflection points where you have f double prime of x change the size. So don't just put it equal to 0, solve for it as 0 and doesn't check the sign of it, because sometimes if it doesn't change the size, it's not an inflection point at all. And you've seen that in my example in I think before the break. Okay, so now slant asymptote. So slant asymptote usually apply for rational function which has the highest power. So max power in px bigger than max power in qx, given that you have a rational function in the form of px over qx. So that's easily see in the previous example of the previous section. You have x squared, I think it's minus x cubed minus x over x squared minus 6x plus 5. Here you have the highest power numerator is 3 and in the denominator is 2. So that's the way that you can identify it if you're given a rational function. There's some more complicated case, but I haven't been like exposed to that much. And I don't think your exam is gonna be like that super freaking difficult because I haven't really seen like any other forms of slant asymptote that is not a rational function. Then after that, you know the fact, then you're gonna, so first step is see this. Second step is to do long division, which you can refer to your lecture notes, or you can see what I think I did this thing before. Well, we have no, it's in 141. So long division, you can look at your lecture notes, apply that technique, or you can like following my examples. I think I have one of the example asking you to find a slant asymptote, where I'm gonna do the long division the way that I learned it in Vietnam in high school. But I mean it's generally the same thing, but it's just like, you know, the way I present it mathematically can be a little bit different. So when you do the long division, what you end up having is that you're gonna have y equal fx. It can be, you know, x squared plus something, ax squared. It can be ax squared plus bx plus c, or it can be mx plus b, or it can be anything. As long as you have the numerator have the highest power than the denominator. In just one case, if you have if you have the result of the long division be like mx plus b in the form of a straight line, and you take limit of x approaching infinity of fx minus mx plus b equal to 0, then usually this is the most common slant asymptote that you're going to see. Because when we say slant asymptote, basically it's just a diagonal asymptote. So it's a straight line, but it's diagonal. So this is the form of a straight line. Usually when you have like ax squared plus bx plus c, it doesn't count as an asymptote. And really it looks kind of really weird on the graph. So if you don't bother about like the problem when you have the result of long division being like second power or any power bigger than 1, because it's kind of like not very realistic to see. So when you take limit of x approaching infinity of fx minus mx plus b, with mx plus b be the result of the long division, and if that limit equals 0, where m is different than 0, m is different than 0, just a condition to make sure that this is a diagonal straight line, then you have that function y equal mx plus b is a slant asymptote, or SA. So that's everything about kind of like concept. Now, from now on to I think next week, it's just gonna be like applying and reviewing to prepare you guys for exam 2. So example 4 is now we find a slant asymptote. So I just put like that exercise from I think section 3.4 to find this. And so we're gonna do long division. So this is plus 0x squared plus 0 divided by x squared minus 6x plus 5. So the way I usually do it is I take the highest power in the numerator divided by the highest power in denominator. So this is x cubed over x divided by x squared is going to be x. So what you do next is that you're going to multiply these things back and change the sign over here. So x with x squared is x cubed. Change the sign negative x cubed. Negative x squared is going to be plus 6x squared. 5x, negative 5x. So what we have is 6x squared minus 6x plus 0. Again, do the division. You're going to continue to divide until the highest power on the left is smaller than the highest power on the right. So you have plus 6, negative 6x squared plus 36x, negative 30. You have 30x minus 30. So what you end up having now is that this thing is going to equal x plus 6. You stop dividing because this power is power 1 and this is power 2. So you stop dividing there. So you have 30 x minus 1 divided by x minus 1, x minus 5. Now slant asymptote. Remember, your domain here is R without 1 and 5. So you can cancel out these two. What you have left is now you're going to find limit of x approaching infinity, fx minus x plus 6. So what you have now is limit x approaching infinity, 30 over x minus 5. And clearly this thing is 0. If you do the same thing for x approaching negative infinity, you're also going to find is this limit equal to 0. Limit x approaching negative infinity, 30 of x minus 5, 0. Again, this is possible because we already identified that our domain doesn't include 1 and 5, and we're just gonna take cancel out x minus 1. So what we end up having is that now we're gonna have the slant asymptote be y equal x plus 6. So very easy, just do this long division. It's kind of like a very new thing to someone, but I mean, if you look at the lecture notes and follow what I did here, or maybe even Google it, there'll be like a tons of information and YouTube videos of how you can do long division. But it's not the main focus here, so I wouldn't really go depth into it. So that is example 4. Now example 5 is example 10 I took from your lecture notes. So I think this is a very helpful practice when you're given all of these parameters and then you have to draw a graph that satisfy all of these things. And if you were able to do it, it does mean that you were able to interpret every mathematical expression that you learned so far in midterm 2 into a graph, and it's kind of like a very good preparation for exam 2. So I put it here and I try to make you guys do it. So first thing is that fx, so trying to identify, interpret these things in all the language that we learned so far, and that can be helpful to finding a graph. So first one, f is continuous on negative infinity to negative 1 and negative 1 to infinity. So it means that the domain of the graph doesn't include negative 1. So just continuous at negative 1 at x equal negative 1. And this can give us a very good intuition that, okay, it might have a vertical asymptote here, and it really does. So vertical asymptote at x equal negative 1. F0 is equal to 0, so you have x and y intercept be at the origin. Limit of x approaching infinity of fx is equal to 3. So you have horizontal asymptote is y equal to 3 when x approaching infinity, and y equal to x approaching negative infinity of fx is negative 3. So x approaching negative infinity. Now x approaching negative 1 is of fx is negative infinity. So this one is the one kind of confirmed here that this is a vertical asymptote. So this is confirmed. And when you have negative x approaching negative 1 of fx is both negative infinity. So I mean, let's say if you have a graph here and this is a special point negative special line x equal negative 1, meaning when x approaching it, it's going to go down to negative infinity on both sides of that asymptote. Then you have f prime of negative 2 and f prime of 3 is equal to 0. So you have critical number x equal negative 2 and x equal 3. And again, when you have critical number, something that usually goes along with it is the extreme value, but not all the time, not always. So you have to put a critical number, and then you have to look at the following data and kind of like information to determine if it's actually is an extreme value or not. Now you have f prime of x positive and negative here, so it's gonna give us something about increasing and decreasing. So I would highly recommend drawing this table out when we have just earlier that I mentioned x, f prime, and f. So you have negative 2 -1, and 3. So these special points. So you have at these two, f prime is equal to 0, and at this one, it's not defined because the function doesn't even include this point. It's positive here, and positive, and negative here, and positive, and then negative. So it's increasing, decreasing, increasing, decreasing. So as we said, you have two max. You can see the fact that you have two maximum here. So both maximum. Next one, again, you have second derivative is equal to 0 as -4 and 5. So again, when you have second derivative equal to 0, you can have an intuition that it may be an inflection point here, but again, you have to check that it changed the sign of the second derivative to have an inflection point. So we have x, f double prime, and then, so you have two special points, -4 and 5, is equal to 0 at these things. So it says it's positive on this one, and negative and positive on this one, and negative on this. Oh, we have the special point 1 here. This is negative. So you can say that it's concave upward, concave upward, concave downward, concave downward, and then concave upward. So we have all of the thing that we need to. So we have inflection point at x equal -4 and x equal to 5, because it changed the sign of the second derivative at there. So now everything is ready. So I would highly recommend for now, you take pictures of everything here. So give me a second. So that you take pictures of what we wrote down here, and then put it on the side with you as you draw the graph with me on in the second slide. And I think it's a very good practice to do that. So I took that, and then now let's go to the next slide to actually draw it. So we know the fact that it's discontinuous at -1. So this is the line that you're gonna draw, and then you already know like where you're gonna approach on the two sides of that. So, and then you have an intercept here, so it had to cross this place. And then you have -3 and -3. It's going to be the horizontal asymptote. -3 and 3. So, and then you have critical number, -2 and 3. Both are maximum. So you're gonna have like a peak here, and then 3 is like here, so you have another peak here, or down here, you don't know. So now look at increasing and decreasing. From -infinity to -2, it only increase. So you have to go this way, up to a maximum. So you're gonna go up and then reach a point, and then it decreases to -1. So it's gonna go straight from this to that, and then on the right it's the same as increase. So it's gonna cross -0. It's gonna cross 0, and then it's gonna decrease at 3. From 3 onwards, it's going to go down. So it's like a maximum there. Again, and then you have concave upward and concave downward. So this is when you start to draw the finished graph, where you try to look for concave upward, concave downward. So you have -4. So it's gonna change from concave upward to concave downward from 4. So I would just draw it at this way. So this is where you change. So inflection point, this is maximum at -2. And again, from on the right is going to be at 5. So 5 is here. So I will put, you're going to go up to a maximum. You change you still concave downward. And it's going to go upward. So this is inflection point. So this is maximum. And again, it satisfies everything now. So the graph is gonna look something like this. Note the fact that you don't have like here horizontal asymptote go down, go up, because it will impose a new interval of increasing and decreasing. And it's the same thing for here. You know the fact that it's not going to be below and then go up to approach it, because you're going to have another interval of increasing and decreasing. It's kind of like similar to the logic we have in one of the example in 3.4. I think it's example 3. Yeah. So that is everything we have, and this should be what you expect in the exam when it comes to 3.5. Like, okay, sketch the curve, and okay, what is the curve of this thing? So that is what you should expect. And this is the graph that I draw just to make sure that I get everything right and do not confuse you guys. It looks something like this. Now, the final example today, and also the last example we have for the midterm 2. So next week it's just gonna be like a general review, kind of like a last minute review of your exam, where I'm gonna maybe like look at your practice problems and put in some of the questions I feel like people did wrong a lot. And again, compared to midterm 1, I feel like not many of you did the practice exam, which I'm really sad, because I think it's a very helpful practice for your exam, but no one actually did it before my sections. And so I would really hope that you guys can do like some part of practice exam, or even all of it, so that I can see where you guys get wrong and I can touch on it on that review. Because if not, it's going to be like kind of like a useless review. Like, you can get some credit for your practice exam, but again, it's not helpful to prepare you for the exam. So just make sure you do as much as possible for that practice exam next week. Now we have this function, and they're asking us to identify the graph of fx. So first of all, domain, intercept. Look at that checklist again, domain, intercept, and then you have symmetry. Then you have, I think, horizontal and vertical asymptote, and slant asymptote, and then you have increasing, decreasing, and all of that. So first, domain. It doesn't, now you look at this is a rational function, and you look at the denominator, there's no discontinuous point. So it's continuous everywhere. So you can eliminate the fact that you can have some vertical asymptote. You have this is wrong, this is wrong, this is wrong. So that's like the first step. Second one, now you look at this increasing, decreasing. So you only have two graphs, and they're different in the way that they decrease and increase. So you look at f prime of x, and you just need to care about the numerator, because the denominator is always positive. So you just check up x, fx, and f. So you have two special points, -1 and 1. And it's equal to 0 at those 2 points. So when you plug in, like, say, a random number, you have this sign, which is going to be, so it decreases on infinity, negative infinity to -1, increase from -1 to 1, and then decrease. So it's going to be this graph and not this graph. So to check back, this is the third step. So when you're going to try to find like the inflection point, and you're going to notice you have inflection point at x equals 0 from here, because it changes sign at x equals square root of 3 and x equals negative square root of 3. So 3 special point, like I think this is here, and this is here. So make sure you do that check back, and then you're gonna find the answer is this one, just kind of like a way to confirm it. So that's everything I have for today. As I said, this is a very curve sketching, and its characteristic of the main focus of exam 2. Try to do as many review problems in the book and review notes as possible, especially the review notes at the end of your lecture notes that I saw. I think those are very helpful exercise for this. And so if you don't have any more questions, I'll end the sections here, and I'll see you guys next week. I hope you prepare good for the exam, and please, please, please do the practice exam. Thank you.